Yeah, well, it was chain rule. Yeah. And one of the students said, I can explain this. So I said, knock yourself out.
Is that good?
Yeah, he did well. Yeah. And the guy who was trying to help, I think, probably understood, or at least he acted like he understood.
I raised your expectations. Actually,
Okay. We are recording. Let's get my slideshow set up. And first, did you have a question? It seemed like you pulled stuff out, and then I got to talking about Clark, and I didn't know if I cut you off from asking your question.
I'm making sure to see if I do have a question.
Okay.
Not really, no.
Oh, okay. Any questions before we get started? Okay. All right. Where we left off last time, we just had begun section 8.2, integration by parts, and I introduced the fact that it's based on the product rule, one of our favorites, right? So the formula expresses, let me back up so you'll see what formula I was talking about. This is the formula. When you're integrating by parts, if you have an integral and you can't think what in the world to do to it to integrate that thing as is, and there's some sort of a product characteristic to it, that you can name one part of that product as a u function and the other is a derivative of another function v, then your integration by parts says the integral is u times v minus, and then reverse those two, the integral of the u. Okay? Now, with letters, it's a little blah, blah, blah-ish, okay? But here's what they're saying. That formula expresses the original integral in terms of another integral, which hopefully the second integral is one you can do, or at least gets closer to one you can do. Depending on the choices of u and dv, it may be easier to find the second integral than the original one. If it isn't, don't do it, okay? You want to always make it easier, except for maybe one or two circumstances, which we'll see. Because the choices of u and dv are critical in the integration by parts process, here are the guidelines that they provide. I think I probably said something similar to this before. See how they work. Try letting dv be the most complicated portion of the integrand that fits the basic integration rule. Then u will be the remaining factors of the integrand. I'm not sure I would quite approach it that way, but we'll see. Then try letting u be the portion of the integrand whose derivative is a function. This is the one I go by. Try letting u be the portion of the integrand whose derivative is a function that's simpler than u, while the dv part, okay, I still would say something else with that. The dv part, when you integrate it to get your v, hopefully it doesn't get any more complicated. That's the rule I use. Note that dv always includes the dx of the original integrand. Of course, the d's go together. All right. When using integration by parts, note that you can first choose dv or first choose u. You can choose them any way you want to. After you choose, however, the choice of the other factor is determined. You can't throw something else in there. It must be the remaining portion of the integrand. Also note that dv must contain the differential dx, which they already said on the previous one in the original integral. Okay. So we're ready for example 1. Find the integral of x e to the x dx. Can you integrate that by just a straight integration? Do you think substitution? Second? No. That's just about, has to be integration by parts. And you got two parts to it, the x and the e to the x. Okay, and of course dx is there too. Which of those, when you take a derivative of it, will get a little simpler, but understanding that the other one, when you integrate it, shouldn't get any more complicated. That's what I
X
go
get
by.
more simpler.
Second?
The x would get more simpler, and the e to the x would.
Yeah. Yeah. Say it again.
The e to x wouldn't get more complicated, but the x.
Yes, when you integrate it, you're absolutely right. So then, let me get my pen set up. Let u equal what then?
Would it be x?
X, perfect. And dv would then be all the rest of it, which would be
E to the x dx.
e to the x dx. Always be sure you include the dx in there. Then, what do you do next? Second? No? Okay. Yeah, differentiate the u. What you get? du equals?
Would it be 1?
1 dx. Yeah, 1 dx, or just dx, right? Pretty simple. That got simpler, right? That's what you wanted. Now we integrate this part, okay? And what does this become? And the antiderivative of dv would be?
We said it would just be e.
Just v, right?
Yeah.
Okay. And when you integrate e to the x dx, what do you get?
E dx.
E to the x. That's why I love exponential functions. They get simple. All right. So now you started with, split it up. The u part you wanted when you differentiate to get simpler, and the dv part when you integrate not to get any worse. Okay? We fit both bills. Now what do we do? Now here's what follow the formula, and the formula is take the product of the two functions. So this thing here is equal to, start with uv, which is u times v
Would be x.
x e to the x. You don't have to do a thing with that. That's just there. Okay? But then it's a minus, always a minus, remember, because you're using the product rule. And the derivative of a product of two functions is the first times the derivative of the second plus the second times the derivative of the first. You're using one of these, subtracting this from the other side. So this is your uv, which you got there. So subtract from that. Now you use the bottom line. Okay? And what's that? E to the x dx. Perfect. E to the x from here, dx from there.
So it's just u times the derivative of v minus v times the derivative of v. So
Okay.
it's just u dv minus v.
Yeah, it's uv, okay. This is u dv is equal to uv minus the integral of v du. That's it, exactly. And your v du is down here, and your uv is across here. Okay. So write it like that, it's sort of easy to remember that way. Okay? Now, all we have to do, this is x e to the x, and what's the integral of e to the x dx? E to the x, okay? But one more thing. Plus c, because that's an indefinite integral. Okay, so you always have a plus c. Now, if this were an initial value problem, which we haven't talked about yet, I would probably choose to call that e to the c, which is, again, just a constant. But I would do it that way because then the rest of the problem will work out a little bit nicer. But we don't have that. C is fine, plus C. Okay. That's how we did it. And that's what they got. So let's see how they approached it. Probably very similar, but they may have thrown a few extra steps in. And it's, I know, but I've got to find you. Yeah. Oh, I'm looking in the wrong class. No wonder I couldn't find you. Okay. There you are. And I think I asked this of the other student. I have a Kaylin Rutledge in my Cal 1 class. Y'all aren't any kid, right? Yeah, she said she thought she knew you. Yeah.
Yeah, we took the trade test.
Oh, I see. And it really confused everybody, right? Okay, yeah, 2 Rutledge. Okay. So let's see. This is example 1. We're in chapter 8, integration techniques and improper integrals. 8.2, integration by parts. Example 1, top of page 524. And we've just done it. Let's see how they did it. Oh, and by the way, just to let you know, y'all lucked out a little bit here. I was talking a little bit with Anil about this beforehand, but we didn't get this far. Yesterday morning, when I started to teach my first class, differential equations, I could not get Screencast-O-Matic to come up. It would not come up. Went down and told, it gave me a screen, which it never gave before, and said, are you using, and it said this, or a site license, or the free thing. And I knew the free thing was just like 10-minute limit, and that wasn't going to work too well. But I tried all 3, and I couldn't get in. They were asking, finally I went down. I told her it wasn't working. Went down again and said, it's asking for a URL to get to the site license. And she wrote it down for me, so I brought it up, typed that in, and then it said, this site license has expired. Okay, so yesterday, first class, second class, third class, I could not use Screencast-O-Matic, so I couldn't upload to YouTube. And the fourth class, just like I had done with the first 3, I just tried it thinking it's not going to work, but it did work. So they did get it done. So we get to use it today. It is working today. But just to let you know, it wasn't yesterday. All right. And this is Preston, right? Okay. So y'all will be able to view this. First 3 classes yesterday will not. But of course, in this, if it ever happens, I leave all the old classes that I've taught before in the playlist of YouTube, and the new ones are always at the bottom, the old ones at the top. Now in this class, that's not all that convenient for you, because the last time I taught this course, I was using a different book. So not many things will line up too well, but at least you'll have something there. Okay. So anyway, we're doing Chapter 8, Integration Techniques, 8.2, Integration by Parts, Example 1, top of page 524. We had already done it. Now we're going to see how they did it. There's an integration we can do. No way to do that just as is, okay? That's not in anyone's table anywhere, I don't think. Maybe it is, but I don't know. To apply integration by parts, you need to write the integral in the form of u dv. Well, y'all told me before, let's let the u be the x and dv be the e to the x dx, which is exactly what they chose. Okay? Or that's the first one they wrote down. You could have written it this way. That won't help you. You could have written it that way. That's really the same problem you had to begin with. So that isn't very helpful. You could have written it this way, and basically you still have the same problem you did at the beginning. Okay? So this is the way that works, because when you take the derivative of u, that gets simpler. You can integrate this, and it doesn't get any worse. In fact, it stays the same level of complexity. So that's the one we're going to choose. You see, if you chose this to be, you integrate that, that's simple. Okay? But when you, differentiate that, it's simple. When you try to integrate this, it gets more complicated. 1/2 x squared over 2. That's what, or 1/2 x squared, or x squared over 2, one or the other. That gets more complicated. So you don't want to do that. And those two don't get you anywhere. Okay? So the guidelines for integration by parts in the earlier slide suggest that the first option, because the derivative of u equal x is simpler than x. It's just dx, and that makes it much easier. Whereas dv e to x dx is more complicated portion, okay? But the main thing is that it doesn't get any worse when you integrate, okay? So, oh, and I see what they're saying. And it fits the basic integration formula, okay? That, to me, is okay. All right, so the dv will then be the e to the x dx. That makes v, when you integrate dv, in other words, integrate both sides, you get e to the x. Okay? Now, they're doing this like this. Then they do u equal x, and that would be du, then it would be dx. Okay? And that's pretty simple. And then your integration by parts produces, and you take the u times the v, that's x e to the x, minus the integral of v du, which the way they write it is the right-hand side. The way I write it is the bottom line. And that will be simply e to the x minus integral of e to the x e to the x minus the integral of e to the x dx, which would be x e to the x minus e to the x plus c. Now, I haven't quite figured out why they always use capital C's for their constant. Most of the time I use lowercase c, and I see no reason to make them capital, but it doesn't hurt. There's nothing wrong with it, but I just haven't figured out why. Okay. And then the other thing they say, and I quite often say it in other contexts, but I don't usually think of it when I'm doing integration by parts. If you want to check and see if this answer is right, take a derivative, and you should get the same integral you had to begin with, which is this. Okay? If you take the derivative of this, that's the product rule. That would be x e to the x plus e to the x minus e to the x plus e to the x minus e to the x goes to 0. That's 0, and yeah, x e to the x. You get what you started with. Never a bad idea to do. Oh, and there's what they say here. To check this, differentiate, and see that you get the original integram, which you do. Any questions on example 1? Okay. I'm trying to see where this is in the text. And I can't see it. So they jumped right to the summary. Okay, that's why I couldn't see it. Okay, so they skip example 2, 3, 4, 5, and 6 before they get to that next part. So let's go back and get those covered. Okay. Example 2. Find this one. The integral of x squared log x dx. Okay? We want to integrate that. Okay? They're jumping right into it. That very first example was one of the simplest ones you could do. This one is going to take maybe a little more head scratching. Okay? What would be your approach to it?
I would take the derivative of x squared.
Okay, so you want u to be x squared?
Yeah.
Okay. So you're saying let u equal x squared. That will require then dv to be log x dx. Okay. Now, here is, this looks great. Looks like a great thing to happen here. Okay? However, I'm trying to think, what's the integral of log x dx? Antiderivative of log x. Second?
Is it not just x?
Let me think.
I thought it.
Derivative of log x is 1 over x. The integral of log x, oh no. I can't think of any function that when you take a derivative, you get log x. There may be one, but I can't think of it right now. So that's the problem with that.
So u needs to be log x.
Okay, let u be log x. I think that might be all right. So this will take a little bit of effort, and it's not bad, okay?
Can we make u x squared log?
I think we're going to head that way, but maybe not exactly with that. But let's do what you said first here, and see, let u be log x, and dv be x squared dx. Okay? Let's head this direction first and see what happens. Then, what's your next step?
Derivative of log x.
Du is equal to, what is the derivative of log x?
Didn't you say it was 1 over x?
1 over x. You agree? Okay. Dx, right? V would then be
isn't it x cubed over 3?
x cubed over 3. Okay? Now that got more complicated, but your first one got a little simpler. Okay? Now, if this works, then your answer here is going to be uv, which is 1/3 x cubed log x minus what? The integral of what? Basically the bottom line here. What is that?
So just be x cubed over 3.
Okay, say again.
X cubed over 3 times
X cubed over 3 times 1 over x dx. Okay? Well, what's the good news here? Now, I'm going to do one other thing. I'm going to pull that 1/3 out front. Is that okay? Okay. I just don't like messing with numbers that aren't going to help me any. Now, what do you notice here?
Can you subtract the bottom x from the top x's and make it x squared?
That's it, exactly. I wouldn't say subtract, I'd say divide into, but that's okay, yeah. Okay, subtract the exponents. Okay, I understand what you're saying. So now we've got 1/3 x cubed log x minus 1/3 the integral of x squared dx. And guess what? We can do that integral. Okay? So let's do it. And what is that? Don't forget the first part, 1/3 x cubed log x minus 1/3. And what does this give us? What does this give us? X cubed over 3. We already did it once, okay, and we're doing it again. And then we finally have a plus C, okay? Now, we can simplify the first part a little bit. It's not necessary to do. We can factor out a 1/3 x cubed and leave us with log x minus 1/3 plus C. No reason to do it, but it maybe cuts down the writing a little bit. Right?
Wait, what did you take out? Oh, you took out
I took out x cubed over 3.
I
I could have written it that way. See, this had 1 and that had 1.
Yeah.
Take them out, left the log x minus 1/3. Not that that's any simpler. Let's see. Okay. All right. Let's see how they did it. No. Well, I mean, it's same answer. But they left it as, they actually wrote the, like I said it, x cubed over 3 log x minus 1/9, or x cubed over 9 plus C. Either answer is fine. And I hope I don't grind this into the ground too much, but to me, that's a, well, multiply those two together. That's a perfectly good answer. That is a perfectly good, correct answer. But if you're doing WebAssign, it's only going to look for one answer. And the other one is going to say it's wrong, and it's not wrong. It's perfectly correct. So, one reason I really don't care too much for WebAssign. Okay. All right. And that's what we got in the book. Ready to do examples? Any questions on that? There is actually, yeah. Example 3, almost without warning, they sneak something really interesting onto you. Now, they do two things. They make this a definite integral, not indefinite, and they also introduce an inverse trig function, okay? So here's your integral from 0 to 1, definite integral here, of arc sine, which I like to say inverse sine of x dx. Now, do y'all recall any functions that when you take the root of them, you get an inverse sine?
It's cosine, or it starts with a C, right?
What's that?
Cosine. Yeah.
Second?
Is it cosecant? Cosecant?
Okay. No, this is not 1 over. This is inverse. So maybe that's why they put arc sine, so you wouldn't confuse that. Now I can take a derivative of arc sine, but I don't know anything that when I take the derivative of it, I get an arc sine. So that almost gives you a hint. Like I said, I can take a derivative of that. So let that be my u. And guess what the dv will be? Let u equal inverse sine. Do y'all prefer arc sine?
Inverse sine.
Huh?
Inverse sine.
Inverse sine, okay. Inverse sine of x, okay? And dv equal dx. That's all that's left, isn't it? Then what's your next step?
Take the derivative.
Yeah, derivative of it, du is equal to. Now, do you remember what the derivative of inverse sine is? It's a messy thing. It's something pretty close to, I'm going to have to check it, 1 over the square root of 1 minus x squared
Oh, yeah. Okay, I remember.
dx. Is that it?
I think it was just 1 over.
Was it?
I
Yeah.
always just remembered it like
Yeah. It's 1 over 1 minus x squared, square root of 1 minus x squared, and then the dx. Okay? Yeah, that's it. Okay? That was the hard part. And over here, what did you get?
This is just dx.
V is equal to x. Just integrate both of them. V is equal to x. Now, that broke one of the rules, okay? Actually, it broke both rules. This, to me, looks more complicated than that. And this is more complicated than that. So nothing got simpler, and nothing stayed the same. But I didn't know anything else to do with this, except take the root of it. So it was almost by default we got this. But what does that give us of an answer, if indeed that's the way to go? What would your answer be?
Inverse sine
Okay.
times 1 over the square root of 1 minus x.
Wait, no. UV. That would just be the V is the x, and the U is inverse sine of x. There's your first part, right? Now, time out. They just have introduced this to you, and you may not realize this. You have to, even though that is not an integral, you still have to evaluate it across the limits. So you have to evaluate that from 0 to 1. Even though it's not an integral, it's the answer to an integral. So minus, and then what's the other part? And again, 0 to 1.
It would be dx over square root 1 x squared with x, right?
Okay, say that a little.
You put du and v together, right?
Yeah, it's the bottom line, and what is that?
Dx over the square root of 1 minus x squared times x.
Okay. How about if I write it like that? Okay? Yeah. It's the product of these two. So I'm going to put the x up here with the dx, and then that is my denominator. Now, it was almost looking like when you take the integral up, you're going to get back to that, but you don't. Because now you have an x up there. And does that mess you up terribly? Why not? What do you do with that? Is that impossible to solve? How can you solve it?
You can't flip it, make it positive, can you? They're all positive.
Okay, I don't
You know how
understand.
there's negative outside the integral?
Oh, I would. Yeah, I like going from 0 to 1. Now, if we weren't doing integration by parts, and that was the problem you had, what would be your first try for it?
Substitution.
Yes, a substitution. Why?
Would you take out the bottom?
Okay, let U be the most complicated part, the innermost part of the most complicated part of your integral,
So just be
which that would be your bottom. And I mean, not just the square root, the inside the bottom, okay? And then look at your numerator. The du would then be almost what your numerator is, okay? And even with the minus sign. So now the minus sign takes care of itself, kind of. Okay, so let's do this. Now, I know in substitution, our favorite thing is U. Integration by parts is U. You can keep doing that. Just remember these are different U's, okay? Or you can use a different letter if you want to. So what you want to do? You still love U's, or you want something else?
We'll stick with you.
Okay, just remember, that's not the same U as you had before. You've already used that one up. Okay, so now in this one, let U be what? Second?
The square root of 1 minus x.
I wouldn't even do the square root. I would do 1 minus x squared. Okay? The innermost part of the most complicated part of the problem. Right? That's it. Then, and what do you do next in substitution? Du is equal to? Second? A little louder?
Or -2x.
Negative 2x dx. You're writing it in differential form, right? Okay? Now look how close that looks to your numerator. What you have to do is just get rid of the -2. So divide it away. Okay? Now, that part, especially if I pull out a -1/2 out in front, that's just going to be a 1/2, as in a positive 1/2. And Corbin, right?
Yes, sir.
Okay. Okay, has anyone else come in since the called roll? Okay. All right. A 1/2 integral. Oh, okay, we still got one thing to do. The x dx that's left is your du over 1 over -2, which we already taken care of that. So that's just du over, and what's in the denominator? What's in the denominator? What's in the denominator? Still got a square root, don't you? But what's inside that?
Is it just u?
The u, okay? Now, one thing we haven't done, and we need to, and again, because it's an indefinite integral, we need to change our limits. These are the limits for x's. We need to change those limits for u. So we take the 0 down here, put x equals 0. What is your u? 1, okay? So this will be a 1 on the bottom. And what happens when you put a 1 in for x here? Not 1 in for x here. Second?
0.
You get to 0. Uh-oh, spaghetti.
No, what did it? Move it 2.
Huh?
-1 squared.
Okay. Okay, what you're doing is placing 1 here to the x. Here's where you define u. 1 for x. You get 1 squared is?
But it's -1 squared, right?
And that's
Oh, you
1.
just put it in some parentheses, basically.
Huh?
It's -x squared, I thought.
That's down here. I don't know.
Oh, okay.
Okay.
Yeah. I mean,
This is what you chose to be the u.
Yeah.
So this is what you plug in.
Okay.
These values for x is here. 0 here gives you a 1. And a 1 for x here gives you
Where's 0, 0? Yeah.
0. Okay. And there you flipped it again. So we're going to have to get our minus sign back again, aren't we? But that's okay. Okay? So what I'm going to do with that is make that a -1/2 integral from 0 to 1. Now, I want to rewrite my integrand, because I think if you haven't been paying attention before, I've said several times, I do not like to use rational expressions if I can get away with it, or radical expressions if I can get away with it. What kind of expressions do I like to integrate? Powers, exponents. Can you write that in exponential form? How? U to the what? -1/2 du. Okay? Can you integrate that? So -1/2 times how?
It would just be
Second? Antiderivative of that. Okay. You keep your base, u, and what do you do?
Is it?
add a whole
Add 1 to your exponent, and that gets you to,
u equals 3 over 2.
second,
Or just +1/2.
positive 1/2,
And then there's u.
and then you divide by that positive 1/2, which is multiplying by 2. And now the 2's go out. Still a minus, but you evaluate this from 0 to 1. Okay? All right. Now we're finally ready to put it all together. Let's first put in the x equal 1 from this first part up here. Okay? I'll do the first part. 1 times the inverse sine of 1 minus 0. And whatever the inverse sine of 0 is, it's still going to be 0, because 0 times, okay. So, then down here, we're going to plug in what this is, and this is the square root of 1. So that's going to be, and it's a minus in front, square root of 1 is 1. Minus a minus, which is plus the square root of 0, which is 0. Okay? Now, I'm going to leave off my leading coefficient of 1. Does anyone remember what the inverse sine of 1 is?
Is it 1?
Okay. Now, when I'm dealing with inverse trig functions, I like to write it slightly differently. Let's just call this, start up. When we have a trig function, you always take what you're operating on a trig function, you're taking the function of an angle giving you a number. And when you do inverse functions, you reverse the order. So this is a number, the answer is going to be an angle, right? Okay? So since it's going to be an angle, let's call this theta, right? Or any other angle you want to call it. I like theta, okay? Good friend of mine, okay? Now, can you rewrite that expression, inverse sine of 1 is equal to theta. I wrote it as a phi, okay? I like phi too, but we're dealing with theta, okay? Theta. Let's rewrite that as a trig function. That little equation up there, rewrite it as a trig equation, not an inverse trig equation.
Would it just be 1 equals theta?
No, sine of theta.
Sine of theta,
Yeah, the inverse of inverse. Okay? Now, can you answer that question? What is theta equal to? What angle, when you take the sine of it, you get a value of 1?
Oh, is it?
Second?
Sine of 90 is that one?
I can't hear you.
90?
90? Yeah. If you're in degrees, if you're in radians, that would be pi over 2. Exactly. So this will be pi over 2 minus 1. And by the way, pi over 2 is a little more than 1.5, right? Because pi is a little bit more than 3. And subtract 1 from it, you got something a little bit more than 0.5 is your answer. And they get 0.5 over 2. And pi over 2 minus 1, exactly like we got. And when they plugged it in, they found that to be about 0.571. A little bit more than 0.5. Okay? That was different on several levels. Okay? First, I try to avoid inverse trig functions as much as possible, but you can do them. And that one, because there's no way to take an antiderivative of inverse sine, take a derivative of it, which you can do, but that puts that being the u, that being the v, and you can go from there. And that didn't mess you up there any, because now you can do the trig substitution to get that answer. All right, does that make sense? All right. There's a little blurb at the bottom of page 525 on that goes from completely somewhere else. and now I'm beginning to wonder why in the world. They have for further information here and it seems to have nothing to do with that technology blurb they have at all. But they do have it here to see how integration by parts is used to prove Stirling's approximation, which, where did that come from? See the article Validity of Stirling's Approximation Physical Chemistry Project. There they give you a source. Okay? Now, why am I mentioning that? Well, number one, it's a potential paper topic. In fact, who was Stirling? That may be a potential paper topic. Or, how did he get to this approximation? And what did it matter anyway? Or, what's the physical chemistry application of this? And all those could be good paper topics. Now, why am I mentioning paper topics? Maybe because this, one of my largest classes that I teach this summer, how many papers have I had turned in yet? None, okay? And we're getting awfully close to midterm. So don't forget you have a paper and start looking for possibilities of what you're going to do. So that's the only reason I brought that up. Okay, I think we're ready to go to example 4. This is also not on the slide set, so let's hit it as well. Find the integral of x squared sine x dx. Okay? You tell me what you would suggest we do, or try, start, whatever.
Can we let u be x squared?
Okay, I like that idea. Let u equal x squared, which means
dv
v is equal to sine x dx. Everything that's left over. You got to have it all in one place or the other. So that's what's going to be left over. Oh, I'm sorry, that's dv. dv is equal to sine x dx. The d's go together. Okay? Then, what's your next step? du is equal to 2x dx. Okay? That got a little simpler. And over here, v is equal to cosine x. Very good. No, that's not quite right. Negative cosine x. Okay? Because when you take the derivative of negative cosine, you get negative of negative sine, and that sure enough is a sine. Okay, and where do we go from here? Notice this is back to be an indefinite integral. So say that again. X squared times, what'd you say?
Negative cosine x.
Okay, so I'll put the minus here, cosine x. Okay, now I'm going to put a minus the integral of the bottom line here, but that has a minus in it, so that's going to make that a plus, isn't it? Okay? And what goes inside the, oh, and I'm going to pull the 2 on the outside too. There's no reason to haul that inside.
Then it's going to be cosine x squared, right?
Say that again?
Cosine x squared.
How did you get that?
Is it, or is it going to be x cosine x?
X cosine x dx. Okay? Now, I'm all right with that first part. That's all right with me. But what do you notice about the second part? You got to integrate by parts again. Okay? So, this is going to be, don't forget the 2. So, what are we going to do here? Okay, and what will it be? Okay. Wait. Goodness gracious, heart attack time. I think I've seen this kid before. Okay. There he is. He is in this class. Okay. Terrell is here. All right. All right. Sorry about that. No, I'm not. Okay. What?
U would be X.
U equal X and dV is equal to
Dx.
cosine X dx. Okay. Then du is equal to dx and v is equal to sine x. Okay. Now we have, don't forget your plus 2. And where do we go from here?
U times V.
Yeah, u times v, which is
X sine X.
x sine x. What's next?
And then the integral.
Second?
The integral.
Okay, but something goes before the integral.
It's
Minus the integral of
sine x.
sine x
dx.
dx. Very good. Okay. Now, I think I'm ready to bring everything down. So my final answer is minus x squared cosine x plus 2x sine x, right? Minus, and remember the 2 still in there, 2, and what's the antiderivative of sine x? Second? Negative cosine x. So that'll add a plus cosine x. And then one last thing?
Plus c.
Plus c, exactly. All right. Good deal. I think that's our answer. You had to use twice because you got to whittle down that x squared till you get to something with no x's in it. We finally got to there with that one. And the sine and cosine make good dVs because they go back and forth, don't get any more complicated. Yeah, introducing minus signs and stuff like that. But
Can you point to where you pulled each one from? Like
what?
Like point. So like the negative x squared.
okay.
Cosine x.
Yeah, this came from the very first, the UV here.
Okay.
And then this came from here, to front of it.
Okay.
That was another UV in the second part. And then this came from where you integrated that, which is number 2, the coefficient for that as well. People at home can't see what I was pointing at, but hopefully they'll follow along. Better to be here, isn't it? Okay, sorry, not everybody can be. Let's see what they finally came up with for an answer. If I can find where they finally came up with an answer. Negative x squared cosine x plus 2x sine x plus 2 cosine x plus c, cha-ching. Okay. Now, when you're needing to do this, making several applications, hey, I've seen.
About the yearly project.
Yeah, I saw that. I haven't had a chance to.
Okay.
When does he need it?
As soon as possible.
Okay.
Because somebody retreat next week or something.
Okay, I didn't know when the retreat was. But yeah, I don't have any office hours on Tuesday and Thursday, so I couldn't do a thing with it yesterday. So I'm going to try to do it today.
You
I
just
have.
told me to
Yeah.
let you know.
Okay.
Thank
You. Okay. Sorry I recorded all that. I should have paused for that, but figure it out at home, okay? Now, but when making repeated integration by parts, be sure you keep the same thing. Don't go and switch them back and forth, because then you wind up right back where you started if you switch your V and D, U and DVs. So be sure you keep your U's the same type things. And hopefully they'll get simpler as you go. Okay? Now, let's do example 5. Any questions on 4? let's go to example 5. Whew, okay, find this one. The integral of secant cubed x dx. Usually they reserve this kind of one for another section, but this one's doing it here, which isn't probably too bad to do. But this is going to take some perhaps foresight to figure out how to break this down best. Now,
I'm not really sure what the integral
what's that?
of secant cubed is.
What's this again?
I'm not really sure what the integral of secant cubed is.
Yeah.
Or the antiderivative.
Yeah. Not anything that comes to mind, is it? And I wouldn't even think of using integration by parts here. I would try to think of something else. But let's see if we can, since it's in this section, and let's see what we can do.
Let's just be like the substitution.
Say this again.
So this just be like substitution.
Okay. What would be your substitution?
It's not like labor stations, it's just like the angle substitutions. Like you just plug in like a kind of like the sine of the inverse sine. We like plug in a 1
Oh, okay. All right. I think I kind of hear where you're going, but and this may be heading in the same direction. What if I broke that into, and there's no real reason to do this, but if I broke it into this, the integral of secant x times secant squared x dx. Isn't that the same thing? Okay. Now, what's kind of good about secant squared x?
It's actually like a factor of
That's right.
isn't it like 1/3?
I think in terms of pairing it with the dx. The secant squared, the derivative of anything. Okay.
Is it cotangent?
No, tangent. Derivative of tangent is secant squared. So there you have a perfect derivative over there. Now, the problem is, when you take the derivative of secant x, it actually gets a little more complicated. But let's try it. Okay? So let's let u equal secant x and dv equal secant squared x dx. Okay? Now, the only reason I'm doing this, I know that what the integral of secant squared x dx is. What did we say it was? That's tangent x. So v is equal to tangent x. I'm hoping that's going to help us. Here's where the rub comes, though. Then du is equal to, anyone know that one? Okay, I'm not going to call your trig teachers and help them.
If you asked me like 2 months ago, I would have had it down.
Oh, it's been a full 2 months? Is that what you said?
Yeah.
Oh, I see. Derivative of secant is strange secant x tangent x dx. Does that ring a bell? Or is that completely foreign? All right. Completely foreign. Let's see if we can find any help here. Trigonometry. Oh, y'all have your books, do you? Inside front cover. Let's see if they do any derivatives here. They don't. Well, let's go back to the derivatives. Derivative of, here we go. Derivative of secant u is secant u tangent u. Okay, so that's what we just got. And derivative of tangent, which we were just doing earlier, and I don't even see it in here. I know it's got to be. There it is secant squared. Okay. And here's just good deal. All right, we're doing example 5 in chapter 8, which is integration techniques. 8.2 integration by parts. Example 5 is this one that we're working on here. So we finally determined what that was. All right, now I'm not sure this is going to work. This is just trying something. So let's see, what would that be if you did your rule here? This would equal, your UV here would be what? Secant x tangent x. That keeps showing up, doesn't it? Okay. And what's that followed by? Minus the integral of secant x tangent squared x dx. Somehow that's not looking a lot better, is it? Okay? So maybe we've gone down a rabbit hole and not really gotten a rabbit. The tendency, my next guess would be break this into tangent x times secant x tangent x, and that inverse it. But I think that's taking us right back where we were before. No, actually, this is the direction we need. Got it. We need a different identity here for tangent squared x. What was that?
Substitution.
No, that's our identity. Y'all seem to remember so well. Now, some of you were in my trig class, and I'm not hearing any loud answers covering your head back there, okay? What is a trig identity for tangent squared? And whenever you see the square, think you're
1 over.
Not 1 over. Pythagorean. They deal with squares, right? Remember your Pythagorean identities? The name anyway, right? Oh yeah, I remember hearing about Pythagorean identities. What were they? Let me do your simplest one, which I hope everyone remembers.
Sin x squared plus cosine.
Okay, there's the one everybody should remember, that sine squared x plus cosine squared x is equal to what? Always 1. Okay? Now, if I want to get a tangent squared out of that, what is tangent squared? Sine over cosine. So let's divide everything by cosine squared x, cosine squared x, and cosine squared x. Okay? And this I know is going to be tangent squared, right? What is cosine over cosine? 1, okay? In this class, okay? And what's 1 over cosine squared? Second?
Inverse cosine. Or no, because secant.
Secant squared, okay? So this is secant squared x. Oh, wait a minute there. So rather than that, now, what I'm going to do is just take this integral, which I don't have much room for, minus integral of secant x, and instead of tangent squared, I'm going to write, oops, I didn't quite get there. Tangent squared would then be secant squared minus 1, right? If I subtract the 1 from both sides. right? Okay, so there's the trig identity we were looking for. Secant squared x minus 1 dx. Okay, that's the one I want to mess with now. Oh, but wait. What does this give us? Minus the integral of secant cubed x. It seems like we've been here before, isn't it? Minus second secant x dx. Okay? Now, I'm not really too upset that we wound up with this. Okay? This is going to be minus the integral of secant cubed x dx. Minus a minus is going to be plus the integral of secant x dx. Okay? Now, you agree with that so far? Okay. Now, the reason I'm not too upset, I can take this and add it to that, and we'll get two of those. And if we can get these other things evaluated, which we're awfully close to, we have the solution for that. Okay? Dividing by 2. The only thing we've got left to do is that. Integral of secant x. How in the world are we going to do that? Well, let's think of another identity that relates to secant x. And we've already used it a time or two. What is secant x? Second? 1 over cosine. So let's rewrite this as the integral of 1 over cosine x dx. Okay? Now, I thought that was going to come out simpler, but I'm afraid it might not. It's not. That's not the way to go. What I would suggest on this one, and this sounds like it's cheating or doing, but actually the other way is just about as bad. On this one, I'm almost certain you can find that in a table. Okay? And if you flip to your table, the integral, basic integration formula, integral of secant x, there it is log of secant x plus tangent x plus c. In front of you? Yeah. I'm sorry. Yeah, what?
I got the wrong case.
The wrong what?
Case 1.
Okay, the wrong test? Is that what you said? Okay. Oh, did I give you Cal 1? Oh, I'm sorry. Yeah, don't do that. I need that back. Okay. I need to give you Cal 2, so are you leaving anytime soon? Oh, okay. Well then, yeah. Did you write on it? Okay, good. Okay. I'm sorry, I didn't mean to do that. Here we have what secant, the integral of secant x is log absolute value secant x plus tangent x plus c. So rather than go through and get that, it's just the log, this answer is log of secant x plus tangent x. Okay? And then we'll have a plus c, but that's going to be at the end of everything anyway. So let's put it all together. And let's see if we can remember where we put it. All right, so here's what we started with. The integral of secant cubed x dx is equal to secant x tangent x minus the integral, and you see we came down and did this one over here, so this is minus the integral of secant cubed x dx, and then we had minus that came out a plus the log of absolute value secant x plus tangent x. Ran out of room, sorry. Okay? Now, what we're going to do is add this integral to both sides, secant cubed x dx plus the secant integral of secant cubed x dx, and that gives you 2 times the integral of secant cubed x dx is equal to is equal to secant x tangent x. I believe that's a plus now, plus the log of absolute value secant x plus tangent x. And then we'll divide both sides by 2 to get rid of that. And there we've solved it. Kind of tricky. But what we did, carrying through what we were doing, we wound up with the same interval we were looking for with the opposite sign. So that means we can add it to this side, get 2 of them, and then whatever the rest of our answer came up with, which is that, divide by 2. Okay? That's a trick. And it works to make it a method. Okay? Now, the other thing is, I didn't show you how to get this, but frankly, it's always in the paper. So just go to the paper and find it. You can, and again, it's a trick. And you can make it work. And once you make it work, then say, okay, I won't do that again. And look up the answer. So let's see if indeed, oh, and one thing I left off, plus C. Okay. Now, what they did that we didn't do is they split it into 2 pieces. 1/2 secant x tangent x plus 1/2 log of absolute value secant x plus tangent x plus C. Frankly, I probably would have done a half C just to keep a half in front of everything, but that doesn't help it any. All right. Now, you'll see other examples like that where you try to solve something, and if you go down, keep going down, you wind up with the same thing you had. As long as it has a different sign to it, go back and add it to the other side, and that helps you evaluate the integral. All right, that was example 5. Let's move to example 6. All right, to erase? Okay. Finding a centroid. A machine part is modeled by the region bounded by the graph of y is equal to sine x, okay, and the x-axis, okay, and that's as long as 0 is less than or equal to x is less than or equal to pi halves. Okay? Now, they show the graph of this, and since several of you don't have books, let me at least approximate the graph here. Sine x does something like this, and this is between 0 and pi halves. That's where it reaches 1 here. So we're trying to find the centroid of this region right here, between sine x and the x-axis between 0 and pi halves. Okay, so we're trying to find the centroid of that. Okay. Now, the first thing they said is find the area of the region. Okay. Well, what I would do is put this into dx's, right? And the area of the region, what would that be? Second? You may have said it, I just didn't hear. 0 to pi halves, perfect. Okay. Because that's what your x is going from and to. And this curve, of course, is the sine curve. So it's the integral of sine x times dx. The height times the width. Sum those from here, do they? Right. The height is sine x. The width is dx. All right. So, this is the area. And what is that area? And the derivative of sine? Negative cosine x evaluated from 0 to pi halves. Okay? And when x equal pi halves, cosine of pi halves is 0. Okay, so the first part there would be 0, negative 0 if you wanted to. The second part, when x is equal to 0, what's cosine of 0? 1, so you have a minus 1. So that has an area of 1. Okay? Okay, done. Now, you can find the coordinates of the centroid, and this was covered back, goodness, in which chapter? 2.7, 2.8, something like there. It seems like it's where you have center of mass, centroid. Now, boy, there's a lot of mess going on here, and frankly, okay, here's my question. I'm afraid I know the answer to this. I bet you y'all are going to need to be finding centroids and things, or are you? I think so, okay. If you're mechanical engineering, I think that would be necessary. Some of you in that. Okay, yeah. So let's go on with it. Okay. What they're focusing here on is the integration, specifically integration by parts. We didn't need it there. That was pretty easy. But they're telling you how to find the centroid. Okay? And basically what your guess here is, it's going to be halfway up each one of these strips, right? Okay? It's just finding the rest of the dimensions here, okay? So of that strip, and of course we're assuming a uniform plate here, that the density isn't changing. Otherwise you wouldn't be looking for a centroid. It'd be center of mass. So this is centroid, meaning you have a lamina, a thin uniform plate. To evaluate the y bar, it says rewrite the integrand, which they haven't told you what the integrand is yet, using a trigonometric identity. And here's another one. Sine squared x, I think is what they're using here, isn't it? Is equal to, and this is basically part of your half angle formula, but not quite there. They sometimes call this a power reducing formula. And it's 1 minus cosine 2x divided by 2. Okay? Now, why did they give you that? Because your integral for your y bar is going to be 1 over a, and we just calculated what a is. A is 1. So that's going to be real easy to deal with, okay? So we don't have to worry about that anymore. 1 over a. And then again, you're doing an integral from 0 to 2 pi, pi halves, okay? Same as before. But now, your y bar is going to be the midpoint of this, which is sine x over 2, right? All along there. So that's the first part of your integral. Sine x over 2. That's your y bar that way. And the rest of it is then sine x dx. Okay? So that's sine x dx. Okay? Now, hopefully this will begin to make sense. The a is just going to be 1, so I'm going to forget about the a now. 1 over 1 is 1. Okay? Integral from 0 to pi halves. Okay? And here's the 1/2. I'm going to pull that on the outside. And here's your sine squared x dx. Okay? And they say use this substitution here. So this is going to be sine squared x is 1/2 of this. So I'm going to pull another 1/2 out. So that would be 1/4. The integral from 0 to pi halves. And instead of sine squared, we're going to put 1 plus, or 1 minus, I'm sorry. Cosine 2x dx. Okay? You're just making that substitution up there in for your sine squared. Pulled out the 1/2 that you had, and then you pull out the next 1/2. That gives you 1/4. So now we have to integrate that. And that would be 1/4 integral from, well, let's see. We don't need the integral sign anymore, I don't think. So let's just do the integration. And what's the antiderivative of 1 dx? It's the antiderivative of the x. X, okay? Minus, what's the antiderivative of cosine 2x? Or just, second? Sine, okay? So that would be sine 2x, but then you've got to divide by 2. It's sort of the anti-chain rule thing when you're integrating, okay? And that will be evaluated from 0 to pi halves. Okay? So it would be 1/4 times pi halves minus. Now, we're plugging in the pi halves for the x here. So 2 times pi halves is 2 times pi halves is pi. And what's sine of pi? Zero. So that doesn't contribute anything. So let's go back and plug in the 0. You plug in 0, that doesn't do anything. And you plug in 0 here, that doesn't do anything. So it looks like it's pi eighths. Okay? It looks like that's all that you get out of this is a pi 1/4 pi halves, which is pi eighths. Okay? And that's divided by 1, which is just pi eighths. I sure hope. Yeah, that's what we get. Now that's your y bar. Okay? We haven't done x bar yet. Okay?
So are the bars, is that just like the
Y bar is the it's the y component of your centroid. Okay. And pi x, by the way, would be something close to 3/8 of the way up. So it's less than 3/4. I mean, less than a half. Less than a half. And that sort of makes sense because there's more function down here than there is up there. So yeah, it looks like the centroid would be a little below 1/2. So pi eighths, that's the y bar. What we've got to do now is calculate the x bar. Okay? Now, what your x bar is how far you are from the y-axis. That's x times the height times your displacement, times your differential. So that would be the integral of x sine x, and I know the dx will be there, okay? Right. And that should be what you need. How do you do that integral? This is going to be your x bar. Now that's 1 over a, the area, but the area is 1, so we don't have to worry with that. But this is the whole purpose for this. This is, let me put this over here. The y bar is pi eighths. Okay? I'm going to erase it here, so he'll have room to work. Whew. This is about the point where hunger kicks in. And we've got a ways to go. I was trying to think. Yeah, this wouldn't be a terrible place for a break. Well, let's finish this problem. But I was just noticing. I'm growling. And again, this is integral from 0 to pi halves, okay, of that. This is the whole reason we're doing this problem now. Because how do we do that integral? Integration by parts with what parts and parts?
U is x.
U equal x, and dv is equal to everything else, which is sine x dx. Okay, then
the
u is equal to
x squared.
huh?
Right.
You're not integrating. It's just dx. You're taking derivative of both sides, and my d just disappeared. Okay, du is dx, and now you're integrating here with v, and what do you get? Negative, is that right? Yeah, cosine x. All right. So what is this based on that? Negative x cosine x. But because you have limits here, this is from 0 to pi halves. Okay, minus, and what's it? What's the second part of this, the integral part? The bottom line down here. Okay, so it's going to be minus, and you had a minus here, so that makes it a plus, the integral from 0 to pi halves of cosine x dx, right? All right. Now I'm rapidly running out of room here. Very alliterative, wasn't it? So is it all right if I erase some of this, even though I've just been using it, but I think we've already used it. So let me get rid of this so we can continue with the problem here. Okay, finally it erased. All right, so let's first evaluate this. When x equal pi halves, what does this give us? A minus pi halves x equal pi halves times the cosine of what? Pi halves. Okay. Now, what's cosine of pi halves? Second? Second? Cosine starts at 1, 0. Zero. Okay, so that doesn't contribute a thing. Okay, that's 0. Okay. All right. Then we do a minus, but you already had a minus, so that'll make it a plus. But then the 0 doesn't contribute anything either, does it? When you put 0 in for x, that's lost. So nothing you get out of this term. Literally, 0 you get out of that term. Plus, and then what's the antiderivative of cosine x? Sine x evaluated from 0 to pi halves. And what's the sine of pi halves? Minus the sine of 0? 0. So that just gives you 1. So your x bar, which is the x coordinate, now remember this is about 1.5, so this is exactly 1. So somewhere about 2/3 of the way out here, that's where your x is. Your y is, well, was pi eighths, which is, something about 3/8, about a little bit short of halfway up. So that's where your centroid is, right about there. Okay? And your area was just 1 anyway, so 1 divided by that. So your centroid for that region was at 1 pi eighths, which would be somewhere about here, I'm guessing. And that looks about right, okay? Because you have less area here than you do here, so it's going to be a little to that side. About 2/3 of the way out. I may have it a bit too far, and a little less than halfway up, because you have more area down here. So yeah, that kind of makes sense. Okay. Whew. Now we're finally ready for our summary. As you gain experience in using integration by parts, your skill in determining the u and dv will increase, meaning practice a lot here, okay? Homework exercises like crazy, okay? The next summary lists several common integrals with suggestions for the choice of u and dv, okay? What would you suggest here?
U would be x to the n, and dv would be
e to the ax dx. Okay, yeah. Because when you take the derivative of this, it gets a little simpler. You just have to do it like n times. And this one gets no worse, except you keep getting 1 over a's, but you can deal with those. What about this one?
x to the n.
X to the n is your u again. You don't have to do it about n times. And sine of ax, the antiderivative, when you integrate once, you'll get a negative cosine. Integrate that again, and you get a negative sine, because we already had a minus sign. Integrate that again, you get a positive. So you just go back and forth between sines and cosines, and every 2 or 3 you flip the signs on it. But they don't get any worse. Okay? Same thing here, only you start at a different location. You start with a positive, and then you go to negative. So there you let u equal x to the n, the dv's either the e's, the sines, or the cosines. Because e's stay fairly easy. Sines and cosines alternate back and forth between cosines and sines. Okay. Now, for integrals of this form, okay, because you can't do a dv with the log in it, that has to be your u. Okay? But the dv then would be 1 over x dx. And one of those 1 over x's will reduce this. So that's the way to go here. Same thing here. You can't use this as a dv, so this has to be your u. That has to be u, that has to be u, that has to be u. Okay? And then your dv will be your x to the n, which is counter to what we did up here, but the reason is these you can't integrate. These you can, and they don't get any worse. These you can't, so you have to do that as a derivative. But these improve when you do take a derivative of them, because now you get an integral form. Okay. Now, what if you had an integral of e's and sines, or e's and cosines? Really doesn't matter. You choose one to be the u. They suggest the u's be the sines and the cosines, and the dv's be the e's. I kind of like that too, because then you don't have to worry about sign changes here. Okay? If you had this being your dv's, then you have to do sign changes. Now, you have sign changes here, but you usually remember the derivative sign changes better than you remember the integral sign changes, because the integral sign changes are backward. Okay? So I like this suggestion, but really you can do it either way. Either way. Because when you're repeating ones, both of them are repeating ones. Okay? But just about always, if you got an E in there, let that be part of the DV. Okay. All right. In problems involving repeated application of integration by parts, a tabular method illustrated in example 7, which we'll do just in a minute, can help organize your work. And this method works well for integrals of this form, where you have u's that are going to gradually go down, and the dv's are going to just get by 1 over a's. That's the only complication. Well, sines and cosines are going to have pluses and minuses. So it works in these forms. So let's do example 7. And by the way, this one is also located at larsoncalculus.com for an interactive version of this type of an example. So let's see, I think they're going to, yes, here it is. All right. So what would be your approach? Okay. Let's do it the old way, and then we'll show it in a tabular way. What would be your approach? Do you have an approach? How about approaching it?
Maybe take the 4 out.
Say again?
Take the 4 outside and make it 1/4.
You can't quite do that here. That's part of the sign. That's your argument of sign. If that was a 4 in front of his, yes, you can do that.
So we'll just make u
Say again? Okay, let u equal x squared, and
everything else would be
dv is equal to sine of 4x dx. Now, when you do the antiderivatives, yeah, every time you're going to do a 4. If that's what you're talking about, that's going to be happening once you do the antiderivatives. Okay, then what? du is equal to 2x. Always have to have a d where there's a d. dx, okay? And v? Negative cosine 4x over 4. That's the over 4 you were talking about, right? Okay. Yeah. Okay. And then your next, so your integral will be a minus 1/4, and maybe that's where you were starting before, x squared cosine 4x minus, but you already have a minus there, so it's going to be a plus the integral of your bottom line here, and that's where the minus wiped out. And here you have a 2x here, but you have a 4 here, so this will be a 1/2 here. Can't pull the x out because that's part of your integral, so this will be x cosine 4x dx. Well, you got to do it again, don't you? Okay? So that's going to be a plus 1/2. Let's maybe not do that yet. Let's talk about that integration first. What's going to be your what? U equal x and dv equal cosine 4x dx. Then du equal dx, and v is equal to sine 4x over 4. All right? Okay? All right. Now I'm going to bring down this first answer. I'm sorry, I keep getting frogs in my throat. Minus 1/4 x squared cosine 4x. And this became a plus 1/2. And when you do your UV here, you're going to get a 1/4 x sine 4x minus, bottom line here is 1/4 the integral of sine 4x dx. Sine 4. Yuck. Okay. Now, minus 1/4 x squared cosine 4x plus, here we have a 1/4 times a 1/2, 1/8 x sine 4x minus a 1/8. And if you do that integral, what do you get? Sine of 4x. Antiderivative of sine. Negative cosine 4x over 4. Okay? Alright, so this then would be negative 1/4 x squared cosine 4x plus 1/8 x sine 4x. Yuck. Plus, minus a minus is plus, 1/32 cosine 4x. Then you have, of course, a plus c. All right, let's see if that's what they get. Now that's doing it brute force way. Minus 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus c. Okay? Now, that's brute force. What they're going to show you is the tabular method, keeping in mind what we had going on there. Okay, so I'm going to erase this, and then we're going to see that their technique, what they call tabular, begins a little easier. Begin as usual by letting, and we just did that, okay? So the one thing I guess. Okay, it's all true. It's just a weird way to express it. That's okay. It says create the table. We start that way. Okay, create the table, and we want to alternate signs. And the reason we alternate signs is because you're integrating sine and cosine, they are going to flip. Okay? Well, no, that's not quite true. And it's also because of your integration. Okay? So, it just says alternate the signs. So we'll do it. Now, this derivative is x, the function is x squared, then the next derivative is 2x, next derivative of that is 2, next derivative is 0. Don't need that, because it's already disappeared. All right, the v prime started being that, sine 4x, and then when you integrate that once, so this first sign is strictly from the uv is positive minus the integral plus minus plus minus. That's why you have those there. Okay. Your u and its derivatives are from here. Okay. And then the v prime and the antiderivatives are over here. The v prime is the sine of 4x. And its derivative is minus 1/4 cosine 4x. And its derivative is minus 1/16 sine 4x. And its derivative, antiderivative is that. And then its antiderivative is this. So you just list those antiderivatives as is. Don't worry about plus these or anything, just list them. The first one and then go. So what we have here is uv. And this was our v, remember? Because that was our dv, this becomes our v. So this times that, okay, minus this times that, plus this times that, and then when you get to here, this is 0, so you stop. So let's see what that yields us, okay? You started with a positive x squared, but this is a minus, so it's going to be a minus 1/4 x squared cosine 4x. Okay? Minus 1/4 x squared cosine 4x. Okay, wait a minute. Oh. I erased it. Sorry. Okay, we'll just go back. Right. Minus 1/4 x squared cosine 4x. Minus, but then a minus here, so it's going to be plus 2x times that would be 1/8 x sine 4x plus, and this is a plus, 2 over 64 or 1/32 cosine 4x. So that's the answer you get this way. And, oh yeah, it was in the book. And that's what we have. Minus 1/4 x squared cosine 4x plus 1/8 x sine 4x, and then plus 1/32 cosine 4x. And then the next time you get a 0, so you just put a plus c. Okay. Solution is obtained by adding the sign products of the diagonal entries. Okay? And that's exactly the answer we got. Okay? So, a little bit easier, okay? If you have one of those forms that you're going to decrease the powers of this and just keep repeated integrations of this, you never use this in your answer. It's just up there what you begin. You use this in your answer because it's UV, and the U is that. We never use the V, UV, and this is your V. And then you just keep going, drop one, and alternate the signs from your plus and minus. Okay. All right, that is the end of the chapter, section. Homework exercises here, any of the odds 5 through 9. They're all three at calcchat.com. Calcchat.com. 5 is at CalcView. Do either 11 or 13 or both. They're both at CalcChat. 11 is at CalcView. Do any of the odds 15 to 33. They're all at Calc Chat. 15's at Calc View. Do 35 or 37 or both. They're both at Calc Chat. Neither are at Calc View. Do 39. That's one of those slope fields. That should be at Calc Chat. And another is 41, and that should be at Calc Chat. Then do any of the odds 43 to 51. They're all at Calc Chat. 45's at Calc View. Then do either any of the odds 53 to 57. They're all at Calc Chat. 55's at Calc View. There's an exploring the concepts 59 and or 61. I'll let you choose those. They should be both at Calc Chat. There is either 63 or 65 or both. They're both at Calc Chat. Do 67, 69. Now here are some proofs, and do these only if you want to. Odds 71 to 75, they should be at Calc Chat. Okay? And then using formulas, any of the odds 77 through 81, and they are at Calc Chat. Area problems, 83 or 85 or both, they're at Calc Chat. And then there's an area, volume, centroid, those kind of things. Any of the odds 87 through 91. Calc Chat. Okay. Try 93 is a Calc Chat. 95 is a Calc Chat. 97 is a Calc Chat. And actually this 99 should be at Calc Chat. I'll let you check that out. Some of these may be getting sort of complicated toward the end. If you don't want to fiddle with them, you don't have to. All right. Any questions? 8-2. That took long enough, didn't it? Okay. Now,
Can you do a little break?
that's exactly what I was going to suggest. We're going to start 8-3. Not a bad time for a quick break, because I need something. My eyes are drying out, clogging up inside, so we will pick up and go from there while it's loading. All right. Still in Chapter 8, Integration Techniques and Improper Integrals. We're going to focus mostly on the techniques. Now we're going to do trigonometric integrals. Now, there are two things that sound a lot alike. Trigonometric integrals and trigonometric substitutions. Two slightly different, well, very different things. These are the trigonometric integrals we're going to hit now.
I was talking about earlier when we had like the,
What's that?
when we had the secant cubed question. I think I was like referring to trigonometric angles.
Okay, you want to go back and ask the question? Is that what you said?
No.
Oh, this is a lot like the secant cube. Is that what you
Yeah,
said?
that's what I
Yeah,
thought.
exactly. That's where, when I said, they don't usually do it here, they usually do it at another place, and that's in this one, the trigonometric integrals. That's exactly right. Okay, so our objectives here are to solve trigonometric integrals involving powers of sines and cosines. Okay? Those are nice, straightforward. We'll solve trigonometric integrals involving powers of secants and tangents. Those are okay. Probably a little more esoteric, and solve trigonometric integrals involving sine cosine products. Okay? And these are going to go back to something that you probably had in trig when they had product to sum formulas and sum to product formulas and that kind of stuff. That's where these come into play. And about the only place I ever remember coming into play. Okay. So the integrals involving powers of sines and cosines. All right. In this section, you'll study techniques for evaluating integrals that are of this form. Sine mx, cosine nx, and then later secant mx and tangent nx, where the m's and the n's are your exponents. Okay? Now, these m's and n's are only positive integers. No negative integers, no fractional numbers, or decimal numbers or anything else, positive integers. To find antiderivatives for these forms, you break them into combinations of trigonometric integrals, which you can apply the power rule. That's the key. Okay? Now, what would be the technique for doing so? For instance, what if you had the integral of sine fifth x cosine x dx? Okay? That's a very straightforward type thing to do. I wouldn't even consider this a trig integral itself. It is a trig. How would you approach that?
Exchange. So are we still kind of doing it like the last time?
Kind of even stuff before last time. Sine x du. Right? This will give you, and then du, derivative of sine, is cosine dx. So this is a substitution problem. Okay? Strictly a substitution problem. Okay? So, and let u equal, yeah, here it is. U equals sine x, du is cosine x dx, and then you have u to the fifth du. Do this, plug back in. Got it. It's just a substitution problem. So, if your cosine or sine is just to the first power, and your other one is to any power you want it to be, then that substitution is going to work. Okay. Now, to break up, what if your m and n, neither one of them is a 1? Into forms which you can apply the power rule, here are the following relationships. This goes back to our good old identities. Okay? Now, if all these are well, here's how you can fiddle with even powers. That fundamental Pythagorean identity, sine squared x plus cosine squared x equals 1. Please, everybody, remember that. That you use all the time. Okay? Now, this one in some small way comes out of that. Okay? Do you want to see how it comes out? If that helps you remember it, you don't. You just want to have the answer. Well, here's the answer. Okay, it's really, they call these power reducing formulas for sine squared and cosine squared. And it's sine squared is 1 minus cosine 2x over 2, and cosine squared is 1 plus cosine 2x over 2. I'm not good at memorizing these things, those signs and SIG and signs and stuff. So easy to cross them up. It's really not an awful thing to know where that came from. Want it real quickly? It does depend on one thing. It depends on knowing, where's my pen? Okay. Do you know your double angle formulas? For instance, cosine, well, let's just say the sum angle formula. Cosine of alpha plus beta. You remember what that was? Cosine alpha, cosine beta, minus sine alpha, alpha, sine beta. Okay? Sort of ring a bell? Well, what if alpha is equal to beta? Then this would be 2 alpha, right? And then this would be cosine squared alpha, right? And this would be minus sine squared alpha. Okay? So here's cosine 2 alpha is equal to cosine squared alpha minus sine squared alpha. Now that, in conjunction with this one, that makes for a pretty, those are fairly similar. Let me change this one slightly and make it cosine squared x plus sine squared x. Okay? That's equal to 1. And up here, we have that cosine squared x minus sine squared x is equal to cosine 2x. Right? Now, if you can remember this one, just rearrange the order of it, and this one, that's not that hard to remember. What happens when you add these two together? The signs go up, sine squares go up. You get cosine squared x is equal to 1 plus cosine 2x. Two of these, 2 cosine squared x equal 1 plus cosine 2x, divide by 2, you got it. Right? And if you subtract these two, this one minus this one, this one minus this one, then the cosine squares go out, and you have 2 sine squared x is equal to 1 minus cosine 2x divided by 2 if you get this. So that's how I don't try to remember, okay, which is the plus, which is the minus. Just use these two formulas, which are easy to remember, and you can derive these in fairly short notes. Okay? So, if you wind up with, I think it's all even powers, and you can't use a substitution easily, do this, and you go from an even power to an odd power. Okay. Make sense?
Yep.
And
what's that second? It's
On
cosine
top.
squared plus.
yeah, I'm sorry, my writing stinks, and you're making fun of it. I get that, but I was writing fast, and it's just reversing the order of them. Sine squared x. Okay. That makes it easier to add and subtract here. Cosine came first here. I'll just reverse these here, and then. Okay. Got it? Okay. Now, didn't realize till now you write with the correct hand. Way to go. All right. All right. Now, here are the guidelines then for evaluating integrals involving powers of sines and cosines. Now, this seems like it's almost mind-boggling to try to keep up with all this, but actually it's pretty straightforward. When the power of the sine is odd and positive, and so far we said they all have to be positive integers, so I don't see why they say that. Save one sine factor and convert the remaining to cosines. How do you do that? If one of these is odd, if the power of sine is odd and positive, pull out one, and then the rest of them are going to be even, right? Okay? And so say if it's squared or fourth or whatever, whatever it is, 1 minus sine squared is cosine squared. Okay? So you can change those to cosines. Then expand and integrate. So this is an odd number, okay? 2k plus 1 for any integer k. That's always odd, because 2 times k, whatever k is going to be even. Add 1 to it and you get an odd number. Okay? And cosine can be anything in the world. Positive, negative, whatever. The nth. Okay. Now, pull out one of these, assign x. Okay? And then what you have left here is, and that's the plus 1 here. That goes here. Okay? Now, what you have left here is sine 2k x, cosine whatever that is. Well, this sine 2k is sine squared raised to the kth power, right? Well, sine squared can be written as 1 minus cosine squared from our Pythagorean identity. Raise that to the kth power and multiply it by cosine to the nth, whatever that was, and then you have sine x dx, and guess what? That's you have everything here in terms of cosines. This is derivative of cosine. You can go from there. This, use your power rule. So. And yeah, this is going to be, could be a long, hairy polynomial, but they're all cosines in it, multiplied by some power of cosine. And then you have all these integrals with all of it, a sine x dx, which is the derivative of cosine, and the sine of the SIG inside. Okay, so that's if the sine is odd and positive, you can always do this. When the power of the cosine is odd and positive, no matter what the thing of sine, do the same thing, you know. Rewrite that odd power as 2k plus 1. Pull one of those out and let that be your d sine, okay? And then this cosine squared can be written as 1 minus sine squared to some power, and you can expand that polynomial wherever you want to. You already had a sine, whatever it was in front, and this is a d sine. So again, you have just some big, long, hairy polynomial formula with all its sines and derivative of the sine. But if both the sine and the cosine are even in powers, and you can't do this technique, even and non-negative, by the way, then you make repeated use of these formulas. The sine squared is this. So this, what I usually do, well, just repeated use of these formulas. Every sine squared, reduce it to a cosine, and cosine squared, reduce it. If they're both negatives, you get down, and soon you'll have everything in terms of cosine 2x's. And to convert the integrand to odd powers of the cosine, then proceed as we have here. Okay? So, kind of a blah, 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 but let's put it into practice and see what works. Okay. Where do you zoom in here? Here's your integral, sine cubed x cosine fourth x dx. And by the way, you might ask yourself, where do you ever run into these things? Are y'all familiar with Fourier analysis? Okay. Trying to think which engineering field uses that really big time. I know electrical uses Laplace transforms a lot. Somebody uses Fourier. I just can't remember which one that is. But it's okay. This is how Fourier transforms look. They're products of powers of sines and cosines. So there are definitely uses for these. So where do you focus here? What is going to be your go-to here? What do you look for when you have the products of powers of sines and cosines? What you want one of them to be? So you can factor out one factor and leave everything else even. Or at least the rest of them even. Okay? And do you see one? Sine. No, the sine is odd, right? Odd power. So what we do, very first step, is rewrite this as the integral of sine squared x cosine fourth x sine x dx. Okay? That looks like it's worse than what we had to begin with, but it's the same thing, isn't it? Sine times sine squared is sine cubed. Yep. Okay? Now, the reason we pulled out that odd one is this is the derivative of cosine, with minus sine included. Okay? So the remaining sine we write as, what is sine squared in terms of cosine? Think Pythagorean identity. Second?
Negative.
Huh? 1 minus cosine squared. Remember? Sine squared plus cosine squared is 1. So sine squared is 1 minus cosine squared. Right? And then this is times the cosine fourth x. And this is a sine x dx. Okay? Don't worry about that sign yet. Okay? Now, let's multiply through. This is the integral of cosine fourth x times sine x dx minus, I don't have to do it this way, but that's why I'm choosing to, integral of cosine sixth x times sine x dx. Now there's a reason I'm doing it this way. Hopefully you may be beginning to see what that reason is. See what I did? I multiplied this times this, got cosine fourth, and then that, and this times this is minus cosine six times that, right? Can you do this integration?
Can we split it up?
Say again?
Can we split it up? Do it by parts?
Please don't. So much easier this way. What's the first thing you did? We didn't even learn it in this course, so we used it several times.
Substitution.
Second? Substitution, of course. That's why we pulled out the sine dx. Okay? So what's your substitution going to be? Let you, second? I mean, whatever you want it to be. I just couldn't hear what you said. U equal what? Cosine x. Then du is equal to? Du is equal to? Help me, help me. Negative sine x dx. And you see, that's why we want the sine x dx there. That's going to be your du. Well, with a sign change here, but it's okay. So we can divide or multiply by minus 1 to make the minus du. So this first one's going to be the minus the integral. It's going to be du's now. And what was your cosine? U. So this is going to be u to the fourth du. Right? Now let's go over to this one. Minus. And guess what? We can do the same substitution. Do you want to still use u, or do you want a different variable? Are you okay with u? Okay. So this time again we'll let u equal cosine x. Then du is equal to? Help me? Negative sine x dx. Okay. So we'll put that a minus and that a plus. Now this will be the integral of, and we're going to have a minus out front, so that makes that a plus. What will that be then? What will that be?
U to the 6.
U to the 6 du. Okay. What's this one? Minus. Pretty easy, right? U to the?
Or, no, U to the 2nd. You just
What's
put them
that?
together, right?
What's that?
You just add them up. Is that what you're doing?
No, these are two separate integrals. That's why I separated them. Okay? I mean, you could do them together if you can remember that, but I thought it might be easier this way. Antiderivative of u to the fourth.
U to the 5th over 5.
5th over 5. Next one.
U to the 7th.
U to the 7th over 7. And then you can put your plus c's out there if you want to. Go back and plug in. And that, remember, your u is cosine. So this would be cosine to the 7th power over 7 plus minus, sorry, cosine to the 5th power over 5 plus c. Got it? See that? All right. Good deal. Now, that's our rendition of example 1. And they left the minus in front. Well, I put it second. I bet your WebAssign would have marked it wrong, but I don't care. So let's clear this out of the way and to see if there's anything different of how they do it. Because you expect to use the power rule where u is equal to cosine x, the reason you're going to use that is because sine has an odd power, cosine doesn't. Save one sine factor to form your du, because the derivative of cosine is sine, minus sine, and convert the remaining factors to cosine. So pull out one of the sine, the other two sines, sine squared, change the cosines by 1 minus. Cosine squared, sine squared is 1 minus cosine squared. Okay? So that's what we got here. Sine cubed x, cosine fourth x is equal to sine squared x, cosine fourth times sine x dx. They just pulled one of those out and wrote it over there with the dx, which we did too. I didn't put parentheses around that. I didn't think that was all that helpful, but then the sine squared, you want it in terms of cosine, 1 minus cosine squared. Cosine fourth is already in terms of cosine. Sine, you leave that because that's the derivative of cosine, plus or minus a sine. Okay? Now you get cosine fourth x minus cosine 6x times sine x dx. And let's see if they break the intervals. Yes, they do, just like I did. Cosine fourth x sine x dx minus cosine 6x sine x dx. And make your substitutions. Well, not yet. I like doing a substitution. They obviously don't. Let u equal cosine x, du would be minus sine x dx. So they put a minus in front and a minus there because they knew that was what was coming. Why? I mean, it's much easier to do it the other way, but it's okay. It changed the sign of the second one. Okay? And then they just said that's cosine fifth, without doing a substitution, minus cosine fifth x over 5 plus cosine seventh x over 7 plus c. To me, the substitution is a far easier way to do it than this way. But this way's right. It's just substitution makes it so obvious. Okay? So there's your answer. All right. Now, they're skipping examples 2 and 3. Let's try to at least do example 2. And example 2 is also, so let's go back. I see this Wallace's formula. The trip we took at the beginning of the term, you remember that first day I was out, we went to Scotland. So when I think Wallace, I think William Wallace. Braveheart, okay. So this is Braveheart's formula. No, never mind. Okay. Let's go back, and I think we'll work on it here. Here's example 2. And like I said, see larsoncalculus.com for an interactive version of this type of example. So here's what we're trying to evaluate here. The integral from, this is a definite integral, pi 6 to pi thirds, that's a pretty small slice most of the time, of cosine cubed x over the square root of sine x, and then we'll do a dx here. Okay? Now, what do you think we're going to need to be doing here? think we can handle it together. Probably breaking up would be all right. Breaking up is hard to do. No, I'm sorry, that's a song. Okay. Second. Power. Yeah, definitely. We're going to wind up with a power rule. Okay. What do you think is going to be to get to the power rule? We're going to have to do a substitution, right? Okay. Which one do you think we need to substitute? Yes, exactly. The innermost part of the most complicated part of the problem. Definitely, denominators are more complicated than numerators. Square roots are more complicated than cubes. And so, yeah, let's go with the sign. So let be. This is where I like to begin. Figure out what the u is. Let u equal what?
Square root sine x.
No, not square root. Sine x. See, the power is going to be the 1/2. So that's where the power rule is going to come. X. Then du is equal to?
Is it negative cosine?
Cosine.
Cosine squared.
Second. What's du? What's the derivative of the sine?
Cosine squared?
Cosine squared?
No.
Where'd you get that? Made it up. Okay. Yeah, okay. Derivative of sine is cosine.
Yeah, okay.
Cosine x dx. All the d's have to have d's with them, okay? All right. Don't make up any harder ones. They're hard enough as it is, okay? All right. Now, so maybe this is what you meant by breaking up. Break one of the cosine off to be with the dx because that's what your du is. Is that what you meant by breaking? Sorry.
No,
I didn't know what you meant by breaking it up. I thought you meant making 2 or 3 integrals. Okay. But no, you're right. Okay. So you were thinking very nicely ahead. So let's rewrite this. And I'm taking extra steps here just so hopefully you can see them. Pi 6 to pi thirds. And we're going to have a cosine squared x because we're going to take out a cosine x dx to go with that, right? Now, if you haven't caught on already, I don't like writing things in radicals and actually even in denominators. So I'm going to erase some of that and have you redo it for me. I'm going to put the cosine squared x here and the cosine x dx there, okay? Now, how would you think I might want to write that? Or probably, I'm going to keep it in this. This is where we're heading. This is just to see I wanted that. How do you think I want to write that radical? You tell me. I don't like writing radicals.
Put sine x in between them.
Second?
Put sine x in between them.
Okay, yeah, that's why I left a gap. Okay, good catch there. But it'll be sine x to what power? To the negative 1/2 power. That's what I want to see. I don't like, oops, I forgot to put my minus sign. I don't like them in denominators, and I don't like radicals. So let's move it upstairs and make it to that. Okay? Okay? We still have a problem, don't we, Houston? I want this here because that's my du. I want this because this is my u. Cosine squared is still an issue. If we can get it in terms of sines, it's not an issue anymore, is it? Can we do that? How?
Would you use a trig?
Say again?
Would you use a trig?
I can't hear.
Trig identity.
I can't hear.
Trig.
My hearing's terrible, sorry.
Trig identity.
Okay, yeah, and what will that give us? Oh, yes.
Yeah, so you would have to. Oh, it would be.
Oh, yes.
It would be 2.
No, not that
All
one.
of those.
Not. Easier.
Oh, so it's just the sine squared plus cosine squared equals 1. We're using that.
Yeah, sine squared plus cosine squared equal 1. But I want that in terms of cosine squared. So what does that
So
be?
then it would be 1 divided by sine squared.
Not divided.
Or,
1 minus sine squared x, right?
yeah.
That's what cosine squared is, right? All right. So now I think I can go on and put the u's in here. Okay? But in order to do that, I also need to change my limits. So when x is equal to pi 6, what is u? Sine of pi 6 is?
6.
Sine of pi 6. I'm not going there, you trick teacher. Second?
15. 15 degrees.
15 degrees. 15 degrees.
Oh, no. Pi 6 is 30 degrees.
That's it. Yeah.
Okay, but what is the sign of that?
It's root 2 over 2.
No, that's pi fourths.
1/2.
1/2, you're right. Okay. Okay, pulling teeth here. Okay. That's a 1/2. I feel like a dentist, okay? Now, pi thirds. What is sine of pi thirds? Second? Root what?
Root 3 over 2.
Absolutely. Root 3 over 2. Okay. And then the cosine squared is going to be 1 minus sine squared, but sine is u, so that's 1 minus u squared, right? Times sine is u, so this is u to the minus 1/2. And then your du is cosine x dx, so that's just your du. See how you got all those pieces in place with the limits changed and all like that. Now, let's deal with that integrand first. Integral from 1/2 to root 3 over 2. Let's multiply that first. U to the minus 1/2 minus, and what's that next one going to be? See, I did that one. That was easy. What will this one be? U to the... Okay, how many halves is 2? 4 halves? Okay. Minus 1/2 is? 3 halves. Okay. Du. Okay. Now, can you do this integration at once, or do I need to split it into 2 pieces? 2 pieces? Okay. So that would be the integral from, I can't read, 1/2 to root 3 over 2.
Well, I guess you could.
Second, u to the minus, huh?
Could you just combine the 2 u's?
Okay, they're different exponents. Yeah, okay.
Let's just do 2
just
pieces.
separate them.
So you do want to separate them? Negative 1/2 du minus the integral from 1/2 to root 3 over 2 u to the 3 halves du. Okay? Can you do this one? What?
When you put sine x back into it.
Not yet, but you can. But I mean, we've already taken care of it by doing this. You know. Second?
Would be 2 u equal 1/2.
Yes.
Oh, so
It would exactly. Okay? It's a power rule. That's what you want to do, wasn't it? Okay? So this will be 2u to the 1/2 evaluated from 1/2 to root 3 over 2. Now these are going to turn out to be some weird numbers. Okay. All right, some really weird numbers. Okay. And the next one, minus what? Integrate u to the 3 halves.
So it'd be
5 halves with, what's your coefficient? 2 over 5, right? All right. And that's going to be evaluated from 1/2 to root 3 over 2. Now, frankly, it was a little messy with the calculus, but not too bad. Okay, pretty straightforward. Doing the calculations really stink. Okay, let's see if we can get them done. This will be 2 times the square root of the square root of 3 over the square root of 2. Right? Minus the square root of the square root of, 1 over, I'm sorry. One over the square root, no, it's not right. Yeah, square root of the square root of 2, okay? Minus 2/5 times the square root of 3 over 2 raised to the 5/2 power. I'm trying to figure out the best way to write this, and I haven't figured it out yet. Minus, I'll put that in parentheses there. And I've got too many square roots there. Sorry about that. That was just a 2. Not square root of 2. Yeah. Okay. Sorry. 1/2 to the 5/2 power. Okay. And I'm trying my best to figure out how they did what they did. Oh, they just left it as that. I'm sorry. They just left it as those powers. So let me go back. Sorry. Now I see what they did. Okay, I was making it more complicated. This is to the 1/2 power, and this is to the 1/2 power. Okay. Okay. Okay, I see what they're doing now. They left the powers of a power in there. So, let's see. This one, we can just write that, and this is what they did. They did leave that as 1 over root 2. And this one, they did 2 to the 5th over root 2. So yeah, their answers do come out the same. It's just a little bit of work to get there, but they do. They left them in the parentheses. I know we're out of time, so that can be done from there. And let's see, that was example 2. And if you figured it out, it's about 0.239. So we'll start next time with example 3. Sorry, that may have taken too long. Homework exercises here in this section will be any of the odds 3 through 13. They're all at Calc Chat. 7's at Calc View. Any of the odds 15 to 19, they're all at Calc Chat. And we'll hold off the rest of those till later. All right, good deal. Thanks. Y'all got your test, right?
No, I need
You need one. Okay. I may give you 2 because you were. No. Okay. Everybody else got a test, right? So have a good weekend. Working on calculus will make it good, right? All right. Cal 2. Test 1. Okay, I know I've got it in. Here it is. Coming up next. There you go.
Thank you.
All righty. Have a good weekend. No. Shoot for a week, but you have to at least get it in before I give the next test out. And that'll be in chapter 8, and we're already in 8.3. We're going to do 8.4, 8.5, and we may do a little in 8.6, okay? And maybe a little in 8.7, and I probably won't do any in 8.8. That's just too long, yeah. So yeah, you got a while, but sooner the better.
Yeah. Appreciate it, Dr.
All right, take care.